Today, we want to revisit a topic that we've talked about a little bit in the past, and that's the relationship between derivatives and graphs. Specifically, what derivatives tell us about the direction of a function and what the second derivative tells us about the concavity of a function. So let's recall some things. The sign of the first derivative tells us about the direction of the function. The sign of the first derivative tells us about the direction of the function. So by sign, I mean positive or negative. So the sign, positive or negative, tells us about the sign of the first derivative tells us about the direction of the function. And when I talk about direction, I mean increasing or decreasing. So direction is increasing or decreasing. The sign of the first derivative tells us about the direction of the function. Positive for increasing, negative for decreasing. The sign of the second derivative, so once again, positive or negative, the sign of the second derivative tells us about the concavity of the function. The sign of the second derivative tells us about the concavity of the function. So concavity, concave up or concave down. Since the second derivative is the first derivative of the first derivative, the second derivative is the first derivative of the first derivative. An all around terrible sentence to write down, but so note the second derivative is the first derivative of the first derivative. We can use this information. The second derivative is the first derivative of the first derivative, and I can combine this with the fact that the sign of the first derivative tells us about the direction of the function. And I can also determine that the sign of the second derivative tells us about the direction of the first derivative. So the sign of the second derivative is telling us a couple of different things. Sign of the second derivative tells us about the direction of the first derivative. I like to summarize this in a couple of different ways. These are the words that go with the idea, and what I usually write down is the relationship between, I'm going to have a column for the function, for the first derivative f prime and the second derivative f double prime. So if the function is increasing, I'm just going to name the function f. If f is increasing, that means the first derivative, f prime, is positive. If the function is decreasing, that means that the first derivative is negative. The sign of the first derivative tells us about the direction of the function. The first derivative can be positive, negative, or also zero, which is neither positive nor negative. So if the first derivative is equal to zero, the function f is flat. That means it is neither increasing nor decreasing. So if the first derivative is equal to zero, the function is flat, which means it's neither increasing nor decreasing. What we want to do is expand this chart to include the second derivative. The second derivative, the sign of the second derivative tells us about the concavity of the function, and the sign of the second derivative tells us about the direction of the first derivative. So if I take this information with f, the relationship between f and f prime, and I start with the direction of the first derivative, f prime, I'll learn about the second derivative's sign. So in the middle, I want this middle column to be my f prime column. And we'll note that if f prime is increasing, that means that the second derivative is positive. If f prime is decreasing, that means the second derivative, f double prime, is negative. We also know that the sign of the second derivative tells us about the concavity of the function. So 2 levels up, if the second derivative is positive, then the function is concave up. If the second derivative is negative, then the first derivative is decreasing, and the function is concave down. If the second derivative is equal to zero, then f prime is flat. And we say, when we say f prime is flat, that just means neither increasing nor decreasing. It could be that the function is changing direction, going from increasing to decreasing. It could, so we have a little maximum, a local maximum. It could be that the function goes from decreasing to increasing, so we have a local minimum. It could also mean that the function goes from increasing, flattens out, and then just continues to increase, so we don't get a minimum or a maximum. We just know that the function is going to be flat because the slope of the tangent line is 0. In terms of concavity, if the second derivative is equal to 0, then the function is neither concave up nor concave down. If the second derivative is equal to 0, oops, wrong color. Then f has no concavity. This is a point where the function might be changing concavity. So this is a possible inflection point. So if the function, if f changes concavity, then f has an inflection point. We call a point on a function when the function is changing concavity, we call that an inflection point. This is a phrase that sometimes gets used in common language when we're talking about trends. You might hear someone say, we reached an inflection point. That means we're changing concavity. So what an inflection point might mean, when we talk about an inflection point, when we've reached an inflection point, a function could still be increasing, but the rate of increase could begin to slow down. So when we think about concavity, when we think about the concavity, we got to remember that concavity is independent of direction, increase or decrease. There might be some situations currently in the news cycle for, say, the past 20 months or so, where we're looking at a function that is increasing. And we want to look at the function, we see that it's increasing because so that means the first derivative will be positive. And we might notice that the function is increasing and the rate of change is also increasing. The function is increasing at an increasing rate. So that would represent a function where the values are increasing and the function is concave up, which means the amount of increase is also increasing. When we reach an inflection point, the values might still be increasing. The first derivatives might still be positive. Oops. The values might still be increasing, but it's possible that the second derivative has gone negative. And if the second derivative is negative, then the first derivative is decreasing. So we could see values that are still increasing, but the rate of increase is slowing down. So we're increasing, but at a decreasing rate. So here are some sentences that help us, that will help us remember the connection between sign, direction, and concavity for the function, first derivative and second derivative. Here's a charts telling us about relationships between the sign of the derivative and the direction of the function, the sign of the second derivative, the direction of the first derivative, and the concavity of the function. The other thing that we want to note is that it's possible to combine increasing and decreasing with concave up and concave down. It gives us 4 ways to combine. So let's look at combinations of direction and concavity. Let's take a look at some combinations of direction and concavity. And we're going to have 4 choices here. Our function could be increasing and concave up, increasing and concave down, decreasing and concave up, decreasing and concave down. So I'm going to break it into 4 categories. We could have f increasing, and f concave up. Oops. Can't all be on one line. I'm trying to make a chart. So across the top, well, let's make a column where the function is concave up, and then a column where the function is concave down. So we can have a function concave up, and we can have a column where the function is concave down. And then in the first row, let's show f increasing. And in the second row, let's show f decreasing. And so here are our 4 combinations. Now, each of these things can be determined by the sign of a derivative or a direction of a derivative. So if f is increasing, that means that f prime is positive. And when f is decreasing, that means that f prime is negative. If f is concave up, then f double prime is positive. And if f is concave down, then f double prime is negative. But the concavity will also tell us about the direction of the derivative. So if f is concave up, the second derivative is positive, and the first derivative is increasing. And if f is concave down, the second derivative is negative, and the first derivative is decreasing. So here are 4 combinations. I'm just taking the same information and we're going to visualize it. And yes, I did just erase pen. So I have a notebook because I was going through too much paper. So if I make a mistake, I can just take a cloth. And if the gel is still wet, then I can just erase it. If some of it doesn't go away, I can use a damp cloth and clean it off. It's because I'm writing on plastic instead of paper. So let's draw these four combinations. In this first row, we want to have f increasing. So I want to go from a low value to a high value. In both cases, a low value to a high value. If the function is concave up, the slopes that I draw at the end or on the right side should be bigger than the slopes on the left side. And so we'll start off with lower values of increase, but then the amount of increase, the slope, should increase. So I want to draw something bent with the concave parts facing up. So it's bent below a straight line connecting the 2 points. If I want to draw a function where we have increasing, I need to go up from left to right, but concave down, this is how we want to put the spoon in the sink. So we don't spray water all over the kitchen. So here is increasing in a concave up and increasing concave down. Notice that the value of the slope at the beginning is much higher than the slope is at the end. We also want to do this in the other direction. I want to go the function decreasing. So that means we end lower than we started. And we want to draw concave up and concave down. Concave up is how the spoon ends up in the sink. Concave down is how we want to put the spoon in the sink. So for concave up, I want the concave part to go face upwards. Remember what's happening when f is concave up. The rates of change should be increasing. So even though the graph is steeper at the beginning than it is at the end, since the function is decreasing, the slope here is more negative than it is at the end. So if the slope here is -10, then it's -5, that's an increase, and then it's down to -1, that's an increase. So the slope is becoming less negative, and that's increasing. For concave down, we just do the same thing, but upside down. We want the concave part to face down. This is how we want to put the spoon in the sink. what we should see when the graph is concave down is that f prime should be decreasing. And we start off with a slope of -1. Now the slope is -5. So that has decreased because -1 to -5 is a decrease. And then from -5 to -10, that's also a decrease. A thing that we want to note about concavity, if the graph is bent below a straight line, then we're looking at concave up. If the graph is bent above a straight line, then we're looking at concave down. So imagine a line connecting the 2 points. Here's a line indicating an increase. Concave up, notice that it's bent below. It's like we grab the straight line connecting the points and pull it down so that the concave part faces up. But when we're decreasing, the same thing happens. The graph shows up below the straight line. I think the reason we chose to describe this as concavity and not convexity is that concave up goes with the second derivative positive. So we like to associate positive with up. If we had called this convexity, then this is convex down. That's when the second derivative is positive. So maybe in the beginning they called it convexity and say, you know what, let's make the up go with the positive. I missed that meeting, so I'm not sure what exactly went on. I just got the memo the next day and like, oh, Leach, we're calling it concavity now. And I'm like, oh, that makes much more sense. And they're like, oh, yeah, you should have been at the meeting. And then I'm like, well, I don't go to meetings. You guys didn't put out an agenda. I ain't going. You know what I mean?
Professor Leach, I have a question, please.
Any questions?
Yes, I have a question, Professor Leach.
Yeah, go ahead.
On the top left,
yeah,
the top left, is that the function is increasing?
Uh-huh.
F prime is positive, isn't it? Correct?
Yes.
And then F double prime is concave up, correct?
No. F is concave up. F double prime is positive. The sign of the second derivative tells us about the concavity of the function.
Mm-hmm. So that one is concave up. And then on the square on the top right.
Uh-huh.
In other words, F, the function increasing, F prime is positive, isn't it?
Yes. The function is increasing. The slope at any point in this graph is going to be positive. So this first derivative is positive.
How come the sign is the one on the top left is concave up, but the one on the right is concave down? Because
we're just looking at how it's bent. So looking at a bend like this, the concave part is facing up.
Is that still the same function? F still increasing, is that correct, both of them?
Yeah, in both of these functions, F is increasing.
Oh, wow, that's confusing.
But this is the difference between, but an increasing function can be concave up or concave down. So in both cases, the function is increasing. In this first column, F is concave up, but in the second column, we're increasing in concave down.
Oh, okay. One of it's increasing, but it's concave up, increasing concave down.
Wow. Right, because this first row is all increasing. First column is concave up, the second column is concave down.
One more thing, how can I tell it's an increased concave down? Is when the F prime is decreasing. Okay.
So, well, yeah. So you can tell if you're looking at increasing in concave up, That means the first derivative is positive and the second derivative is positive. Or you can see that the first derivative is positive and the first derivative is increasing. So there's two ways to determine concavity. These three things are connected.
Okay. You don't mind go one more time, the one on the bottom, the bottom left and bottom right. So the function is decreasing. F prime will be negative, correct?
Correct. If the function is decreasing, f prime will be negative.
And then the f double prime will be concave down.
No, f
Decreasing, concave down.
f is concave up. In this square, f is concave up, and in this right square, f is concave down.
Oh, right.
Not f double prime. F double prime is negative. F prime is increasing. F is concave up.
I'm sorry, the on the bottom square to the left,
Yes.
it's decreasing with the concave.
Don't say it.
Oh, I'm sorry. Decreasing concave down. Is that correct?
What's decreasing?
The second prime.
No.
I mean, f double prime.
No. F is decreasing.
Yes. Mm-hmm. And
F
then
prime is negative, and F is
right.
decreasing. That means the same thing.
Uh-huh.
F is concave up. See how the F is decreasing because the values are getting lower, and F is concave up because the bend. So the bend is facing up. We could put stuff into this bowl. The spoon is
Yes,
up.
when you said concave up, that's f double prime, isn't it?
No.
No, it's
F
still
double prime is positive. F is concave up. You keep saying F double prime is concave up, and that's not what we're saying.
I see.
The function F is concave up.
It's decreasing concave up, correct?
F is decreasing, F is concave up.
F decreasing, F concave up. On the bottom right, the function F is decreasing, F prime is negative.
Yes.
And then how can I tell
F is decreasing and F prime is negative.
Yes.
And the other thing that's going on in this square is that F is concave down, F prime is decreasing, F double prime is negative. That's what's going on in this square.
Okay, I will look it further. It's kind of confusing. Thanks, Professor Lich.
So here are the four things that could be going on in a function. A function could be increasing or decreasing. A function could be concave up or concave down. And here's what here are four visual representations of what's going on. Remember that the sign of the derivative tells us about the direction of the function. If the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. Increasing in both of these cases, decreasing. If the function could be increasing or decreasing and still be concave up or concave down. That's why we have four squares. If the function is concave up, that tells us that the first derivative is increasing and also that the second derivative is negative. So in both of these cases, whether the function is increasing or decreasing, both of these graphs show f being concave up. Any questions? It only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail.
One more thing, Professor Lich, I think I almost get it. So on the f double prime, if it's positive, then if it's a positive on the f double prime positive, then it's concave up, isn't it correct? Then
that wasn't complete. You use the word it, and I don't know what it
I'm
refers
sorry. F double prime is positive, then the f function will be concave up, correct?
That's it.
Okay, and
We gotta
then
make sure we don't get to use the word it, because
right.
does it refer to the function, the f prime, or the f double prime?
And
If
then on
f
the
double
right,
prime is positive, f is concave up.
right, on the right side, f double prime is negative, then the f function is concave down, but it depends, concave down, it could be increasing or decreasing. Wow, it's so confusing. I see it now, thanks.
Okay. Use the word it again. When f is concave down, f double prime is negative, and f could be increasing, or f could be decreasing. All right, so there's lots of ways to remember this stuff. So here's a visual representation of 4 combinations of increasing and decreasing, concave up and concave down. Some from column A, or actually some from row A or B, and then some column, let's say column 1 and 2. Or we might want to remember connections this way. If f is increasing, f prime is positive. If f is decreasing, f prime is negative. If f is concave up, then f prime is increasing and f double prime is positive. So the best thing to do would be to review all these facts to make sure that you have it all in order. And then draw pictures of combinations of increasing, decreasing, concave up, and concave down. So what we want to look at today is what we can do with the function. What we can do if we actually have a function in our hands. What we're going to focus on is to find out when a function is, when say a first derivative is positive or negative. We first need to know where the first derivative is equal to 0. So first we look at where f prime is equal to 0, because that's where it might be changing from positive to negative. And then the same thing will happen with f double prime. We want to know about the concavity of the function. We're going to first have to look where the function has no concavity. So let's take a look at an example. Let's suppose that f of x is, let's see, I think I have this on decimals. I think I just lifted this right from the book. Oh, so thief. So let's take a look at this function, x cubed minus 9x squared minus 48x plus 52. Now, for a quick analysis of this function, switch over. Let's take a look at the graph of this function. So we'll grab our favorite graphing calculator, Desmos. And we see what the function looks like. It's a cubic function, so we expect it with a positive leading coefficient. So we expected this up, down, up again pattern. We expected the graph go up, down, up again. It's a cubic function, has a positive leading coefficient, so it definitely goes up when we're headed to the right and down when we're headed to the left. A cubic function will have at most 2 terms, and so this one has both of those 2 terms. So we can see where these things are happening. So there's a high point at -2, 104, and a low point down here at 8 at -396. Also notice that around the -2, we can see that the graph is concave down. It's bent downward. But when we get to 8, the graph is switched and now it's concave up. So somewhere between -2 and 8, it must be changing concavity. It looks like it happens around 3 maybe. At some points between -2 and 8, the function has changed concavity, going from concave down to concave up. We want to find out when those things happen. So let's take a look at our function and find some derivatives. So we need to look at the first derivative for intervals of increase and decrease. So f prime is 3x squared minus 18x minus 48. What we're going to do is we're going to set f prime equal to 0 and solve. We'll look where the derivative is 0, and then in between those points, that's where it'll be increasing or decreasing. So what we're going to do is solve f prime of x equals 0, and in between those points, the function will be increasing or decreasing. I'm going to solve f prime of x equals 0. In between those points, f will be increasing or decreasing. Because if f prime is equal to 0 at the 2 points that we know we're going to find, when f prime is equal to 0, it's neither positive or negative. So in between those, the function will be increasing or decreasing because f prime will be positive or negative. So that's why I want to take the first derivative, set it equal to 0, and solve. And we happen to know exactly what's going to happen. So I'm going to take my 3x squared minus 18x minus 48. And set it equal to 0. I can divide out of 3 or factor out of 3. And what we're really looking at is an x squared minus 6x minus 16. And then I can factor this further to x plus 2 and x minus 8. So I get 2 points where the function is flat. We're saying setting f prime of x equal to 0 and solving. So now we can see that f is flat when x is equal to -2 and x is equal to 8. In between -2 and 8, and outside of before -2, in between -2 and 8, and after 8, we should see the derivative either being positive and then negative or negative in those 3 intervals. I rewrote that sentence twice halfway through the sentence, and that was a bad idea. It came out really weird. These 2 values of x, -2 and 8, divide the number line into 3 regions: before -2, between -2 and 8, and after 8. In those 3 intervals, the derivative will be positive or negative, and that means the function will be increasing or decreasing. So the -2 and 8 divide the number line up into 3 intervals. At these values of x, the first derivative is equal to 0. And so we got 3 intervals: before -2, after 8, and in between -2 and 8. F prime is equal to 0 at -2 and 8. So it has to be all positive or all negative in between those values or outside of those values. And once we figure out what F prime is doing in these three intervals, we can use that to figure out what F is doing. So for each of these three intervals, we want to determine if F prime is increasing, is positive or negative, so that we can determine if F is increasing or decreasing. All right, this is what we'll take a look at tomorrow. For today, I want you to remember these four pictures, these combinations of increasing, decreasing, concave up, concave down. All right. That's going to do it for today. I'll see y'all on tomorrow. Everybody have, oh no, that's going to do it for this week as well. I'll see you all on Monday. If you have questions, then you can send me an email along with the time that you'd like to meet tomorrow for office hours. I need to have an email with a time in it so that I know when to make sure I'm on. All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend, and thanks for playing.